Greetings from Greece. I hope all the participants to be healthy, strong, and all countries deal with pandemic COVID-19. My name is Vasilis Halimisis and I'm a PhD candidate at Electrical and Computer Engineering Department at National Technical University of Athens, Greece. Today, I'm going to present you our work with title a zero point 0.6 volt 3.3 nanowatt adjustable Gaussian circuit for tunable kernel functions. I am very happy to be attending for second time and helping with reviewing procedure for the first time in IEEE SBCCI conference. The outline of our work is presented in this slide. It includes the following. Firstly, I will introduce you in the term of Gaussian function circuit, or as it is also called bump circuit and its main applications. Then I will present you the first bump circuit which was implemented by Delbruck. Furthermore, the proposed architecture will be presented and analyzed. The next step is the theoretical analysis in which I will provide you the basic concept, extra information of course you can find in our work. In order to confirm the proper operation of our circuit, we implement the layout and post-layout simulation are provided. Last but not least, comparisons and conclusions. Radial basis functions are a especially useful tool in mathematics with a variety of applications ranging from mathematical approximation to, and of course, interpolation to engineering applications. RBFs, or as they called, are extensively used in machine learning. In RBF neural networks, which perform effectively in classification and function approximation problems, the activation function of hidden layers neurons is an RBF. Also, they are used as kernels in non-linearly separable cases of support vector machine (SVM) algorithm, in which kernel tricks allows operation in high-dimensional feature space. Analog integrated circuits are widely used in various fields and applications. Except from Internet of Things (IoT) applications, there is a new trend in which analog computation methods are used for machine learning and artificial intelligence applications. Analog IC architectures have the advantage of low power consumption, low area, and precise parallel computation due to the physical properties of analog circuits. Data classification and regression problems are solved by machine learning methods, many of which are used on Gaussian functions as activation functions. These functions can be easily implemented in hardware by analog circuits, which are well known in literature as bump circuits or Gaussian function circuits, as I already referred. The design of Gaussian function circuits generally aims to independent tunability of the Gaussian curve's three characteristics, which are height, center, or as it is called mean value, and of course width. In addition, such circuits should be ultra-low power and low area due to the fact that in system-level implementation of multivariate kernels or radial basis functions, neural networks with many neurons in each hidden layer, many bump cells have to operate in parallel fashion. There are different applications in which Gaussian function circuit can be used as basic building block. For example, support vector machine, K-means, RBF classifiers, RBF neural network, and of course in many sensor applications. Delbruck's simple bump circuit is presented in this slide. It is the first implementation. It consists of only 8 transistors, which form into basic building blocks: the current correlator, which are the PMOS, and the differential pairs. Current correlator consists of 4 PMOS transistors. The Gaussian function is produced by the current correlator output current and shows the similarity between the differential pairs I1 and I2. The NMOS transistors are a typical differential pair. Delbruck's simple bump achieves tunability in height and center, while width is determined by the effective W over L ratio of the transistors, which also affects the height. There have been, of course, several implementations of Gaussian function circuit, many of them inspired by Delbruck's simple bump architecture, of course. The most compact Gaussian function circuit consists of only 4 transistors, but it lacks with tunability. There is a variety of complicated architectures which are synthesized using the transilinear principles and the exponential characteristics of the subthreshold MOS. Also, their architecture consists of extra stages, for example, transconductors, D2A converters, floating gate transistors, and of course current mode circuits. Delbrug's simple bump circuit can be modified to achieve electronically and adjustable width independent of other bump parameters. This is achieved by the proposed architecture in this slide. It consists of a differential block and of course a symmetric current correlator, which is different in comparison with Delbrug's one. The presented architecture provides a typical Gaussian function curve. The Gaussian curve's height and center are tuned via bias current I bias and parameter voltage VR. In this curve, we also have the ability to adjust the Gaussian curve's width via parameter voltage VC applied to the bulk of the differential block's transistors. It results in a shift of the differential currents along the vein axis by altering, of course, VC. In practice, in system-level implementation, using such Gaussian function circuits as building blocks, the input and parameter voltages are generated by previous blocks of the system, such as could be, of course, D2A converters or sensor systems such as analog circuit extraction blocks in active pixel sensors. In this work, of course, we have a motivation by Delbrug's simple bump and proposes a new architecture of an ultra-low power, only 3.3 nanowatt, low voltage, of course 0.6 volt, bulk control, 14 transistor Gaussian function circuit architecture, for of course tunable kernel function. In this work, we add of course 4 external transistors, Mini 1, Mini 4, MIPI 5, and MIPI 6, and we use bulk control techniques based on triple and well NMOS transistor. All bulk control transistors provide us independent parameters tunability by using current parameters, current and of course by using only circuit parameters, current and voltages. In our paper, a mathematical analysis of the proposed bump circuit is presented. All transistors operate in the subthreshold region, and we use the MOS model based on book analog VLSI circuits and principles. We have 2 equations, one for PMOS and one for NMOS. Vg is the transistor's gate voltage, Vs is the transistor's source voltage, Vd is the transistor's drain voltage, and last but not least, Vw is the bulk or body voltage. The other parameters are Vtau, which is the thermal voltage, kappa P and kappa N, which are the slope factors for PMOS and NMOS respectively, the characteristic current IOP and IONE for PMOS and NMOS respectively. For every transistor, we use a scaling factor M to capture the relative W over L bar U according to transistor dimensions. The third expression is current correlator expression. Equations 1 and 2 are numerically solved using MATLAB, fsolve function, and current correlator equation. The proposed Gaussian function circuit behavior is presented in this slide using previous equations. We achieve a good tuning of the theoretical output current via parameter Vc and constant I bias and VR parameters. In this slide, the Gaussian function's behavior is presented for constant Vc and I bias for various VR values. This means that the center tuning of the theoretical bias current via VR parameter is achieved. The height of the theoretical output is set by parameter I bias, as shown in this slide, for constant Vm and VR parameters. The Gaussian circuit simulation results are from post-layout simulation. The layout of the proposed architecture is shown in this slide, where the area is 38.9 micrometers multi 50.3 micrometers. By increasing the bulk voltage Vc, we achieve higher transistor transconductor GM values. This results in more current flow for I1 and I2 as shown in this slide. As a result, the deviation or width of the Gaussian function output is increased, as shown in this slide, without affecting the amplitude and mean value. Only an increase on transistors' body voltage leads to a width increase. The height of Gaussian function's output is set by the bias current I bias, as shown in this slide, for constant VM and VC voltages. The increase in bias current achieves an increase in the amplitude of the Gaussian curve. All these results are from post-layout simulation. The mean value of the Gaussian curve is altered via parameter VR, as shown in this slide. The maximum output current is achieved when input voltage is equal to parameter voltage, Vin equal to VR. All previous slides confirm the proper operation of the proposed architecture. We can implement multivariate kernels. Such kernels architectures can be realized with two or more bump circuits connected in a cascade fashion. Only the first bump is biased with the current I bias, while the output current of each bump cell is used as the bias current of the next bump cell. Each one has its own parameters and input voltages, of course. The 2D implementation confirmed the desired scalability of the proposed circuit. The sensitivity behavior has been evaluated using the Monte Carlo analysis tool for n equal to 100 rounds. The corresponding histogram for the bump circuit center of voltage is shown in this slide. Also, the corresponding histogram for bump cell height of current is shown in this slide. Both confirm the proper sensitivity behavior. The proposed Gaussian function circuits and characteristics in comparison with previous work related is presented in this, of course, table. We have the performance and the characteristics. The implementation with the minimum number of transistors is presented in 10, but it lacks of tunability in width. The topology with the minimum bias current is presented in 15, but it has high voltage supply. We have, of course, an ultra-low power implementation and low power consumption, as you can see in this table. A compact, ultra-low power, low voltage, 14 transistors Gaussian function circuit has been presented in this work. The proposed circuit accurately emulates Gaussian function with adjustable center, height, and width. Both theoretical analysis and post-layout simulation results demonstrate the proper operation. Of course, it could be used as a building block for hardware acceleration of machine learning algorithms. Thank you very much for your attention. Please do not hesitate to contact me. Questions, please.